So Professor Dr. Sabu Thomas has about 37 years of experience working in the area of macromolecular science and green composites for a wide range of technological applications. He currently holds the positions of Vice Chancellor of Mahatma Gandhi University and the Founder Director and Professor of the School of Energy Materials. The floor is yours, Professor Thomas.
Thank you, Chair, for the kind introduction, and many, many thanks to Professor Mao and team for the kind invitation for the very exciting conference. This is my first visit to Egypt. I'm really excited. I'm going to talk to you about nanostructured polysaccharides for water purification. Basically, I will focus on nanocellulose in my talk. You can see a beautiful picture of nanocellulose. My university was started in 1983, commemorating the father of our nation, Mahatma Gandhi. And dear colleagues, today is the Independence Day of India. The 75th Independence Day of India today, actually. And Mahatma Gandhi fought for the freedom of India. This is the part of my region. You can see the small circle. I belong to Kerala, the southern part of India. And dear colleagues, if you look at the fresh water we have, less than 1% of world's fresh water is accessible for all direct human use. You can see a blue color letter. So we have only a very small amount of water, and this water has to be preserved, to be reused, to be recycled. I have a very interesting slide here. You can see the waters. Do you have a laser? You see, you can see the water, scarce region. Yes, you can see the water scarce region here. You know, Africa, northern part of Africa. And if you look at India, India is going to be water scarce region in 2025. And if you look at the population, in 2000, look at the water scarce region only 3%. And now look at in 2025, 7%. So we have to really find out new methodologies to purify water. If you look at the water purification techniques, we have chemical technique, biological techniques, and mechanical techniques. And if you look at the water purification membranes give a lot of possibilities because membranes are capable of giving right type of porosity, good mechanical properties, flexibility, warm and hydrophilic character. So membrane offer a lot of possibilities for water purification. And if you look at the different types of purification, the microfiltration, ultrafiltration, nanofiltration, many people spoke about different types of separation process. And if you look at reverse osmosis, is get rid of all the pollutants. Here we have a beautiful picture. Here you can see if you're doing microfiltration, you can remove E. coli and oil particles. If you go for ultrafiltration, you can remove viruses and proteins. If you go for nanofiltration, you can see the small compounds you can remove. And if you go for reverse osmosis, you can remove everything. You can remove ions. And when you look at the different types of polymer membrane, there are PVDF, polystyrene, PES, polyacrylonitrile, there are a variety of membranes. But dear colleagues, membrane filtration has a big problem. The fouling is a very big issue. Fouling process because of organic absorption, fouling process because of colloidal material, scaling process, biogrowth. There are many, many issues. Dear colleagues, today I'm going to focus more on nanocellulose. Nanocellulose is a very interesting material because it's hydrophilic, and you can do wonderful chemistry on the surface of nanocellulose. If you're a good chemist, you can do good chemistry. Nanocellulose could be manufactured. My laboratory, they make nanocellulose. You can make low nanocellulose, or you can make nanocrystals. The former, speaker spoke about nanocrystals. So these synthesize both nanocellulose and nanocrystals in my laboratory. And if you look at our synthesis protocol, my PhD students collect all this agricultural waste. We go for alkali treatment, mild hydrolysis or a strong hydrolysis using acid. You can make beautiful nano. It's a very simple process. And you can do a lot of chemistry on the surface of nanocellulose. You can do esterification reaction. You can do tempo-mediated oxidation process. You can do polymer grafting on the surface, relation reaction, cationation reactions. Several reactions could be performed on the surface of nanocellulose. We also do electrospinning with the nanocellulose. That gives a lot of possibility to control the porosity. We can do several reactions to control hydrophilicity or hydrophobic nature of the surface. Now, dear colleagues, I'm going to show you some of our work with my PhD students. Initially, what we did is we looked at the commercial filters in the market. If you look at the commercial filters in the market, they're all bilayer construction. The bottom layer is a non-woven structure, over which you have an electrospun PVDF. And what we did is we tried to modify the commercial filters using nanocellulose dispersion. So we made nanocellulose and we coated nanocellulose on the surface of commercial filters. We also did a small chemistry on the surface of nanocellulose. You can see this is nanocellulose. We reacted with melt of acid. So very simple chemistry. And we could introduce CO minus group on the surface of nanocellulose. After doing this, you know what we did? My PhD students coated the commercial filters with the nanocellulose dispersion. You can see our coating. Once you do that, look at the separation of crystal violet. Crystal violet is a very important textile dye, and we try to separate the crystal violet using modified nanocellulose. You can see all the crystal violet has been retained the surface of the top surface of the filter. And you might ask, what is the reason? The reason is electrostatic interaction between the modified nanocellulose and the crystal violet. That's a simple reason. That's why we could get rid of all the crystal violet. You can see this is a commercial filter. The separation efficiency is much lower. But if you use chemically modified nanocellulose coated filter, look at the separation efficiency, quite high. Similarly, a PhD student of mine, we had a cooperation with Slovenia. My Slovenian collaborator was interested to remove indigo carbene dye. When she used PVDF, the efficient separation was 22.2%. You know what we did? We made a hybrid structure, PVDF and nanochitin together. Nanochitin we made from the craft shell. And you see, once you hybridize, and when you once you do the electrospinning process, you know the separation efficiency 88.9%. Hybridizing PVDF with nanocellulose. I will show you another interesting example. You know, water is increasingly contaminated with a lot of suspended particles. What we did is, we took the commercial membrane and coated the commercial membrane with nanocellulose dispersion. I can show you an example. Look at this. All this suspended particle were stopped at the top surface of the filter. The filter was coated with the nanocellulose. And this is the bottom part of the filter. You can see this is made of PVDF, the bottom part. So all the suspended particle could be separated. You can see the impure water, the pure water after filtration process. Let me show you another example. This is the work of Finnish group. Nanocellulose would be utilized for purifying seawater. You know, seawater is increasingly contaminated with oil because of the sinking of ship. What if, the group in Finland did, they made nanocellulose aerogel. Then the aerogel has been coated with GU to make it hydrophobic. Look at this slide. This is actually the aerogel. The aerogel is coated with the GU to make it hydrophobic. You know what happened? All the oil in the sea could be absorbed by this aerogel because aerogel surface is hydrophobic. And aerogel cannot take water because water is hydrophobic. And once you do that, either you can press the oil out You can reuse it or you can burn it. And the Finland researchers actually commercialized this technology using nanocellulose. Let me show you another example. Nanocellulose could be utilized to remove heavy metals in water. You all know that water is increasingly contaminated with heavy metal. But if you want to remove chromium, chromium-6, which is negatively charged, what you have to do is you do a small chemistry. React to the polyvinylamine nanocellulose. When you react to the polyvinylamine, you can introduce massive amino group on the surface of nanocellulose. Then you can catch all the chromium. Similarly, dear colleagues, we can remove nickel, cadmium, lead. So all heavy metals could be, separated from water using nanocellulose. Dear colleagues, we can also remove bacteria and viruses. To remove bacteria, you coat the filter with nanocellulose, the hole size becomes small, so small. So all the bacteria could be reached at the top surface of the filter. But if you want to remove viruses, they are very small. We are all suffering from, the coronavirus. Viruses are small. If you want to catch viruses, what you have to do is to react nanocellulose with polyvinylamine. Introduce massive amino group on the surface of nanocellulose. And then you can have electrostatic interaction between the virus, it's called negative charge, and the nanocellulose. So we can remove viruses. We can remove bacteria using nanocellulose. Now let me show you another important example.
We have 3 minutes left. Yeah?
Yes, I'm going to finish. Then we can have more discussion. Nanocellulose is a very interesting material to reinforce commercial electrospun membrane. Probably you all know that commercial electrospun membranes are quite weak mechanisms. I can show you one example. Look at this is a commercial electrospun membrane of polyacrylate fly. The mechanical strength is very weak. If you coat one surface of these membrane with nanocellulose, you see where we stand. The strength goes up. If you coat both sides of the nanocellulose, the red one, the strength further. So all the electrospun membranes could be made stronger by nanocellulose coating. My concluding remark, nanocellulose and nanochitin are very exciting material. You can renewable, you can make from the nature. And my group is strong enough to make all this in our laboratory. And you can tailor the functionality very easily by doing good chemistry. You can do electrospinning of nanocellulose. You can do a lot of wonders with nanocellulose. And you can remove heavy metals. We can remove bacteria and viruses. We can remove, all sorts of dyes. Now we are trying to remove, MAWA dye. We are going to try to remove other contaminants of water. So this is a very exciting field. Give hope for the water. And I would like to thank all my colleagues, collaborators worldwide, including Professor MAWA. And I'm the editor of Nanostructures and Nano Objects. If you're working in the area of nano, you can submit your article to Elsevier Journal. That the size score is now 10. And we are also quite active in publishing books. We have a variety of books on nanocellulose, water purification. And this is my group in Kerala. So most welcome to Kerala, to my laboratory. And this is our nano group. And this is some beautiful pictures of Kerala. We have beautiful pictures of Kerala. Most welcome to Kerala. Thank you so much.
Thank you so much, Professor Thomas, for the very exciting and very interesting, liberating presentation. Now the floor is open for questions. We have 2 questions.
Thank you, Professor Thomas, for this nice presentation. Yes, nanocellulose and nanoactin is very interesting and also aerogels. But I want to ask about the fouling. Do you feel that the fouling and the absorption efficiency and the generation for these aerogels and for the nanocellulose and the coating surface, I know the mechanical stress is being enhanced. What about the founding?
Yeah, this is a very interesting question. You see, nanocellulose incorporate, the fouling could be decreased. That's the fouling could be decreased. That's a very important point, particularly nanocrystals we incorporate. We incorporated nanocrystal to some of our systems. We found that the fouling could be decreased. And one more point, we also did some graphene oxide in some of the systems that we are actually developing a new material. Incorporation of small amount of graphene material into nanocellulose, the fouling could be dramatically reduced. This is a very important point.
Another question.
Yes.
Well, thank you, Doctor, for the interesting presentation. I admire the wide range of applications you realize. This is great. But one problem I don't understand, why we go to cellulose application? Isn't this one step back in this technology with the general use now of polyamide material, chemical resistance, temperature resistance, and all the advantages of this material?
You know, this is a very interesting question you asked. Nanocellulose you can extract from all agro waste. That's the beauty of this material. You can easily get nanocellulose. You can from straw, from all agricultural waste, you can make nanocellulose. This is renewable and eco-friendly. You know, I'm able to synthesize nanocellulose. We start the 100 grams of straw or any of the anamorphic dried material, you get something like 50 to 30% of nanocellulose. Pardon? Cost. Oh, if you manufacture and buy, gentlemen, you can definitely reduce the cost.
Gentlemen, I would highly recommend that you continue. Yes, sure. No, but we have other questions. Harder question.
Actually, I'm asking about membrane capacity.
Pardon?
Membrane capacity value. What's the membrane capacity?
Membrane capacity value. We haven't really estimated the membrane capacity value.
Oh, yes.
We haven't done the membrane capacity value. I can get you the facts and all the details I can give you.
Also, I didn't see the dimensions of the nanocellulose. The dimensions.
Oh, okay. You see, nanocellulose, the diameter of nanocellulose is 20 nanometers. And the length of nanocellulose is actually several micrometers. And nanocrystal, the length of nanocrystal that was made was 150 nanometers. And the diameter of the nanocrystal was 18 nanometers.
Also, I'm asking about the membrane reactivation.
Okay, these membrane could be, see, this is again a very interesting question. These membrane could be reactivated. These membranes could be cleaned and you can use it several times. We have used up to 7 times these membranes. Yes.
We have a chair question.
Yes.
Thank you very much for this presentation.
Thank you.
All of us now would like to work with Nancy. Presentation. As you know, that the extraction of Nancy from the agriculture waste or agriculture source, there are different methods which may you get different characterization of nanocellulose.
Right.
So this is maybe good points, but also another challenge with the performance of nanocellulose with membrane according to different method of extraction. Because as you know, that could be fibers, could be particles, and also the coating of one of the slides you have mentioned, the coating of the membrane with nanocellulose. I don't know what about the adhesive force between the nanocellulose and the membrane, the polymers, more reactive together or not. So if you can just
This is again a very interesting question. Interface addition of nanocellulose with membrane substrate. So the best way of tackling this problem is some sort of chemical treatment. If you can do that, you can make the interface adhesion quite strong. Otherwise, after series operation, nanocellulose could actually peel off from the surface. So we also did some chemistry on the surface to make the interface strong. Very interesting question.
last question.
Yes.
If you generate an electrostatic reaction between viruses or any charged molecule on the surface,
Right.
and surface,
Right.
how do you guarantee the stability of the actual viral molecule to the surface of the nanostructured membranes? Are you sure that the virus is stably adhered to the surface?
We have tested
Okay,
some of these.
how would you adhere the virus?
Yeah, this is again a very important question. These might get destabilized, right? Reaction. Once it's interacting with nanocellulose, the virus get destabilized. And
That is really very important issue if you go for virus concentration and vaccination reduction. So if you wanted to kill virus, concentrate and produce a very high titer, you don't be able to do that.
yes, exactly.
Thank you so much.
Thank you.
Yeah, it was a pleasure actually.
Thank you so much. Yeah.